Hello, so good afternoon. Thanks for being here. Few students are coming, so they will arrive a little bit later. Today we start with our presentation related to the InRel-NPower project. After the very nice introduction of yesterday from Peter, we have seen that the major roadblock today for the gallium nitride is material and costs. So we need the material with a very good quality, and we need a cost as low as possible, comparable with silicon or even lower. So today the first two presentations will deal with materials. So Joff and Elke will speak about material, how it can be, we can produce the substrates, and how we can do of very good quality. The last one, Farid, will speak about how to make device from these substrates. So this we are really going into the depth, in the heart of our project, of the activity of our project. I hope that you will enjoy it. So join me to welcome Joff and to speak about materials for gallium nitride electronics. Joff.
Okay, thank you, Gaudencio. Maybe just a few words about myself. I'm an electrical engineer by education. I have my PhD from the University of Ghent on the topic of MOCVD growth, so it's on the topic. Then I was at IMEC for a few years, until in 2010 we created a company, Epigawns, where we in fact manufacture gallium nitride epi wafers for all kinds of electronic applications. Enough about myself. Today I want to talk to you about the material properties of gallium nitride. I will go very fast in that because Peter has already told a lot about that. So you will see some things that you have seen yesterday already. But then I also want to talk to you about epitaxy in general and epitaxy of gallium nitride specifically. And I will say a few words about gallium nitride on silicon. What are the challenges there? So first, yesterday, gallium nitride was introduced as a kind of new kid on the block in power electronics. But in fact, the material has been around for already 20 to 30 years for optoelectronics. So it is the material that you all know for the LED lights that you have at home and in your car and wherever. And one of the critical aspects of this technology is that with gallium nitride, you can achieve very high efficiency. So it is the plot here where we have plotted the luminous efficacy. So it is the efficiency with which you convert electricity into light, but adapted for the human eye. And because an LED has a very narrow spectrum, you can really only emit light where you need them, where you can see them. So you can see, compared to any other kind of technology, the gallium nitride does much better. This was recognized in 2014 because the Nobel Prize of Physics was then awarded to these three gentlemen here, which really proves the value of the technology in general. Now, why is gallium nitride such a good choice for optoelectronics to start? One of the main aspects is that gallium nitride is not just one material, but in fact it is a complete family of materials. You can see it here. You don't only have gallium nitride. You can add aluminium, really increase the band gap up to 6.2 electron volt. And as was explained yesterday, that gives you this very huge electrical field, critical electrical field. So it gives you very good properties for power. Now for optoelectronics, if you replace part of the gallium with indium, you can really tune the band gap so that you can have emission all over the visible band of the spectrum. Now, an LED is a very basic structure. It's a PN junction where in between you squeeze these indium gallium nitride quantum wells to have the right wavelength. And one of the things that people noticed very quickly was that in order to have this very highly efficient emission, you needed to make the quantum wells very thin, so only 2 to 3 nanometers. And the reason for that is that if you look at the band diagram, it seems that the wave functions for the holes and the electrons are spatially separated because of this built-in polarization effect. So it was really shown in practice that there was polarization in the system and that it had some negative effects. So we turn into polarization. This was already shown yesterday. So first, gallium nitride typically is a hexagonal word-side lattice. There is a cubic variant, but it's not very common. And if you look along this C-axis, so the vertical axis, you can clearly see that there is separate planes that are consecutive of the group 3 metals, and then the nitrogens on top. So it's really a consecutive stack. And so if you look at what are the necessary conditions for polarization, one of the main things is that you need your crystal to be non-centrosymmetric. So there cannot be a single point in your crystal across which you can mirror and have the same situation. And clearly, because of this layered stacks, this is not the case for the word side. Now, on top of that, if you look at the constituents of this crystal, so we have gallium aluminium on the one hand, nitrogen on the other hand, typically 50-50%. You can see that the nitrogen is really the special element on the block because it's very electronegative, so it is one of the big balls here. And it's also a very small size if you look at the atom-to-atom bonding. So compared to the other elements, it's really quite different. Now, if you put everything together, so we have this non-centrosymmetric crystal, we have the very large differences in between the elements themselves, so it's very easy to see that you will have charge separation along this C-axis. Moreover, this spontaneous polarization, if we look, aluminium is even more different from nitrogen than gallium. So the polarization effect in aluminium nitride will be larger than it is in gallium nitride. And also, what was shown in one of the first plots is that the bandgap energy of this aluminium nitride is also much larger than the one of the gallium nitride. So if you put that all together, so imagine you have a very thick gallium nitride layer, and you grow on top a very thin aluminium gallium nitride barrier that has a strain relative to the gallium nitride, a higher bandgap, and a higher spontaneous polarization. You create a picture like this, and your bandgap diagram will have this bending because of the polarization effects. You have the bandgap offset, and you create this quantum well there. Very important is that you create this quantum well without any impurity doping. So there is no scattering sources for your electrons. So the mobility in the structure is naturally very high. Values were named yesterday. 2000 is, I guess, a very relevant number there. Also, briefly discussed yesterday is that you have various possibilities for this barrier material. Typically, you go from GaN a little bit up to all GaN. You can also do pure aluminum nitride, or you can do indium aluminum nitride that is lattice matched to the gallium nitride on top. And if you plot these materials as function of thickness, you can see that for instance, a very thin aluminum nitride barrier, you get values up to 10 to the 13th, which is about double compared to the standard Algan situation. And with the indium aluminum nitride, you have the possibility to go a little bit thicker. You can have even higher MSs, which gives you tuning parameters to play with. Now, now that we know how such a structure is created, typical epi wafer will look like this. We start from a substrate, silicon carbide, sapphire, what have you. Here on the top we have this gallium nitride, aluminum gallium nitride barrier configuration that gives you the active part of your device. And in between we will need to grow a buffer. I will talk about the buffer, what are the necessities. Basically what we want to do there is compensate the differences between your silicon substrate and the 3 nitride material on top. What's also plotted here is passivation, because passivation is crucial in this technology. I will also say a few words about that. Now, with such a structure, you can make the lateral device. What you need is 2 ohmic contacts to contact the 2-dimensional electron gas, and a gate in between to modulate the current in between the two. Now, one important aspect, I think that was also pointed out yesterday, is that we have these polarization charges that are larger in the aluminum gallium nitride than in the gallium nitride. But these charges you cannot use in your transistor, because these are ionic charges. They are fixed to the crystal. They will not move. So in order to create mobile electrons that will be attracted there in this quantum well because of the configuration with the band gap and because you have higher positive ionic charge here than there, these electrons need to come from somewhere, and you need to have, in fact, charge neutrality across the whole structure. And very early in the gallium nitride technology, it was recognized that these charges must come from the top surface. Now there is one issue with this, the fact that your charges of your electron channel come from the top surface, and that is that if somehow during your processing or during operation or whenever you change the charge on the top surface, you will immediately also change what's happening inside your transistor. And that, of course, is an effect that you do not want. So this is a calculation that was done by van der Walle. So this is really first principle calculations on what can exist on the top surface of such a structure. And it is clearly shown that for a number of given configurations, like the ones here, the gallium dangling bonds and so on, you do create states in your band gap that can give up these electrons into your channel. So any imperfection here can be a source of these electrons, can be a state that donates electrons to your source. Now, I already hinted at this unwanted effect of the surface charge. Imagine you have a transistor source gate drain, where next to the gate you have an area where this surface charge is in a situation that you cannot control. So meaning that when you pinch off the transistor, somehow this charge goes into a certain given state, so that the moment that you want to turn on the transistor by pulling up the gate voltage, this, what they call virtual gate, is still in the pinch-off condition, meaning that even though you want to turn on your transistor, it does not react to what you want. And this was something that was mitigated by Prunty very early on. It was shown that you can grow silicon nitride on top of this, and then have these silicon electrons act as a kind of surface donors to emit electrons into the channel. And the reason why I have plotted this one here is because if you have a configuration where you terminate the surface with nitrogen and you then have the silicon atoms on top, in fact you can, now we have drawn the end of the crystal here at this level, you can in fact consider that the gallium nitride crystal is now extending till there, with the only difference that now you have replaced group 3 elements with a group 4 element. And of course a group 4 element on a group 3 place is really an element that will donate its electron. It's a kind of impurity doping in effect. But of course, in order to do that, you need to have this very perfect atomic configuration at your surface, which is why this topic has been studied for over 10 years in detail to get this particular thing right. Okay, that was the brief introduction of the material properties. I don't think there was too much new there. I want to now talk to you about epitaxy. And first we need to understand what epitaxy exactly is. So if you look on Google, you will find this explanation here. And basically what we are going to do is we are growing an existing crystal with additional material. That being said, the new material can either be the same as what you have, or it can be different material. And the best explanation is in fact just this very nice TM picture here, which is work from already a very long time ago, where you see it's a gallium arsenide, aluminum arsenide superlattice. So these are materials that have quite a different lattice constant and band gap. But still, if you look at the lines of the atoms, you can see that the crystal is perfectly continued as you grow up the structure. And this is really, I guess, the key definition of epitaxy. This is what we want to do, just make one crystal with different materials inside. So in order to do that, at Epigan we use the technique that is called MOCVD or MOVPD. Basically, the name is explained. Metal organics is because our source materials are typically molecules like this, 3-metal gallium or 3-metal aluminium. So it is a compound where you have a metal combined with this organic metal groups. That's where the name is coming from. Vapor phase epitaxy means that we are working in the gas phase. So it's really a gas phase process. So typically a reactor looks like this. We have a susceptor where we put substrates on top. We will heat this up to relatively high temperatures for gallium nitride. Some will say it's low temperatures if you do aluminum nitride, but still we are above 1000 degrees. And then we insert these reagent gases, so the metal organics, and for nitrogen we use typically ammonia as a source. We emit that here through this shower head so that in the area above the substrate we can have some reactions. There are other techniques that can obtain the same. One example is molecular beam epitaxy, where your source materials are really the atomic sources. So it's a block of gallium or a block of aluminium that you use to do the deposition. Another possibility is HVPE, where you in fact carry gallium from a melt into your reactor with a chlorine carrier gas. However, practically in production, everybody is using MOCVD because it has a number of very clear advantages. The growth rate are reasonable, crystal quality is quite okay. Important is we can make atomically abrupt interfaces. And as we're going to do heterostructures, this is of course crucial that these interfaces are sharp. Alloying is very easy, and you can even do production-like reactors that give you reasonable yield. So in that sense, it is quite an interesting technology. On the downside, as you have seen, these precursors contain carbon or hydrogen. So it is very likely that some of these atoms also end up in your layers, in your crystal. So you have a very clear source of contamination. Okay, and then if you want to do really special things, it will be tough to find a quality precursor. Now, I wanted to point out a few critical aspects of MOCVD technology. It is a very brief overview of a rather complex technology. So there's a number of different aspects I want to point out. First, we are working in the gas phase, so you will have to deal with fluid dynamics. The example we have here is, again, a rather old reactor where you have the gases coming in from the top and they are pumped down to the bottom. And here you have a heated susceptor where your substrate will be. And because you have two opposing forces, name it being the forced convection down and then the convection because of the temperature difference up, you get this very funny flow patterns in your reactor. Needless to say that this is not a commercial model of reactor. Now what I really wanted to show is this plot here where they in fact do the same thing. So it's a horizontal reactor now. So we have here the susceptor is this block here, it is heated. And the gas is introduced from the left to the right. And what you can clearly see, what I wanted to point out, is that here above the susceptor, there is a boundary layer. There is a layer where you do not have these white particles. And it's a very important concept in MOCVD because in this boundary layer, you have a temperature gradient and a concentration gradient, which are both crucial to controlling your process. So that is mainly what I wanted to say of the fluid dynamics, is that we need to take into account that this one exists. So if you then turn this situation and you look at the chemical reactions, you have to, I'm not sure if this is very clear, you have the boundary layer where your source materials have to diffuse through, where you also have a quite significant temperature gradient. And as the source materials, like this 3-metal gallium, diffuses to the surface, it will start to pyrrolize. So it will lose some of these metal radicals in the gas phase because of thermal decomposition. So that on the surface, really, you end up with a monometal gallium and a flavor of ammonia that may be losing one of the hydrogens or not. So that at the surface, after pyrolysis and diffusion, you have this reaction here. So it is monometal gallium ammonia, and it goes to gallium nitride and methane and hydrogen. These are produced at the site of reaction. Now, very important to understand is that this reaction, it's an equilibrium reaction. So you can push it either way. You can go from gallium nitride this way, or you can go from the gas phase that way, just depending on how you control the thermodynamics of your reactor. So it is not a given, it's really an equilibrium reactor. And of course, we will control this, the direction of this process by controlling what happens in temperature, pressure, and especially the vapor pressures of the sources. Another important aspect, I'm slowly building up to some movies that will make everything clear, but I need to explain it like this first, is the kinetics of the MOCVD growth. And again, there you have an equilibrium between particles that reach your surface, you have migration across the surface, and then you have competition between either desorption, where you lose the precursor, or incorporation in the crystal, which typically happens at a step, so at the edge of an atomic step. This can either be because your crystal has some off orientation and you have natural steps on the surface, or it can be in these islands, these nucleation islands that you have already formed before. So, consequence of this, if you grow on a foreign substrate that has no steps of its own, nucleation technique is really crucial to get your growth started. Again, there will be movies that will show this in practice. Now, how does this really work? Yesterday you had to remember the Poisson equation. Today I want you to go back into your thermodynamics course, which I will not go into detail because it is a little bit out of scope. What we will be talking to you is we start from enthalpy and we define the Gibbs energy. The Gibbs energy is the one that matters for you. It has enthalpy, it has temperature, and it has entropy. So entropy, you know, there's also a lot to say about that, but it is again crucial in the crystal growth. Now, we forget about the previous slide. What we want to do is describe this epitaxial growth system by the means of some state function. Also there, we have a choice. We can choose one or the other. We prefer the ones that have pressure and temperature as variables because they're the easiest to work with. You can also choose, for instance, Helmholtz with the volume, but in practice, creating a reactor with variable volume is not easy. Now, what we want to do is define a reference state for the system, which can be anything, and it's denoted by this 0 there. And then based on that, look what deviations to this reference system will do. And from that, you can derive from this Gibbs energy a chemical potential. And this is the one I want you to remember for the next 5 minutes because it will come back. So this is the one. Important, it has temperature and it has the logarithm of this difference of pressure over the reference pressure that you have defined there. So this is the one really that you want to see. Now, how does growth work? It is very simple. It works with the Gibbs free energy or this chemical potential. So we have an ambient, so you have a reactor ambient where you have certain pressure, temperature, vapor phases of the gases, and you have your crystal. Now, if the chemical potential of your crystal is lower than the one of the ambient, you will have growth. It is that easy. That's all I wanted to say. If you understand that, that's how it works. Now, also the opposite way, if you manage to make the potential of your crystal higher than the ambient, it will also start etching. Typically, the main things that we will work on to do crystal growth is we will work with a positive pressure differential between the ambient and the crystal, which we call supersaturation, and a negative temperature difference, which is undercooling. And with that, first a practical example. This is work that was done by this Japanese gentleman in the 60s, and he plots here as function of undercooling and oversaturation of water in the gas phase, how you can grow snow crystals. So it is really empirical. He studied what the effect of these things is on the shapes of your crystal growth. It goes from 2-dimensional to 3-dimensional in all kinds of various phases. So it really works. But as promised, I wanted to show you the movies. So these are movies from these people here at Bell Labs in the late 70s. So I apologize for the quality of the movies. They are a little bit dated. But still they, I think, illustrate what I tried to say before quite well. So what we will do is show the growth rate as a function of this logarithm of the pressure over the reference pressure. Remember the expression for the chemical potential, it's this that you are changing. So you change the overpressure of your thing. And we will work for the first two movies at 2 different points, so 2 different values of this oversaturation. So we start with the first, and one of the things I want you to look at is we will have nucleation, so we will have islands forming on the surface. There is such a thing as a critical dimension for such an island so that it maintains. And so what I want you to do is pick out one of these islands that will be formed and try to see how it behaves in practice. So this should start by itself. So we have growth on a very flat crystal, and you will see the atoms impinging. So we are working here on this particular oversaturation point. And then we will see how the atoms behave. It should start any time now. So we have them here, and you see there's clusters that grow and then disappear again. Like this one here, it's gone. You have this one here. Will it maintain? It's exciting. Yeah, this one reached critical dimension, and it will be remain. And then what you also will see is that you have these different nucleation sites. The longer you grow, you will see that they will start coalescing towards each other. So that's really how the first layers of the crystal start. What you can also see here is that on some of the existing islands, you already have a second nucleation site starting. So even though you have started from a perfectly flat crystal, you already start seeing some topology forming. It's inherent in the way this thing grows. And so in the end here we have almost full coalescence of the first layer, and then it will just continue with the next few layers. So also I did not point it out, so the critical size for one of these islands under these conditions, let's say it's about 10 to 15 atoms in this simulation, which will be different in the next movie where we will have a different overpressure. Okay, so this was movie 1. Movie 2, we do the same, but we have much larger oversaturation. And so, one thing to notice is that the critical size of these islands now is much smaller. It is much more easy for one of these small things to go into a large one. I think now the limit is about 5 atoms or something already. Of course, also because of larger oversaturation, your growth rate speeds up significantly. It's much faster as in the one before. And the third aspect of this is that the roughness is worse than in the first case. So it is much easier to create a 3D surface. Okay, so that was the basic thing. The next 2 movies, there will be 2 new concepts that I want to introduce. The first is contamination. So epitaxial growth is very sensitive to contamination, and we will first have a similar movie as what we have seen before. So we have the nucleation, and the black atoms that now appear are contaminants. So they are atoms, for instance, oxygen, that very easily bond to all the rest. And you can clearly see that these impurities act as nucleation sites for all these islands. The islands preferentially are around one of these contaminants, which is maybe a little bit misleading because you may think this is a beneficial effect. It will help you for nucleation. That's why we need to wait for the second movie. where first I want to show you Stepflow. So Stepflow is in fact the regime that crystal growers prefer to maintain smooth surfaces, and it is shown here. It is the case where you have in fact equidistant steps on your surface that then grow by moving from the left to the right. And the advantage of this regime is that you can continue it forever and forever while maintaining a perfect surface morphology, being the best case that you can have one atomic step. So this is really what, as a crystal grower, what you want to achieve, this step flow. Now, what will happen at a certain point is that, again, they will introduce contaminants into this step flow, which will be the black dots. They are coming now. And you should see how the black dots interact with one of these steps. So in between, your step flow just continues, but here at this one, it is really blocked. So the contamination really stops the propagation of this step flow across your surface. And the result of that, I think we need to look in a little while near here, is that you can see that then all these steps will catch up with one another. It's called step bunching. So it's really, instead of having one atomic step, you will have 3 or 4 at the same time. And then, of course, your surface is again destroyed. I think it will happen here. It is not as fast as I thought. Let's see where it is. I think you can see it here. So here you have 1, 2, 3 steps all at the same point. So it's really how the crystal growth is now disturbed by the contamination. Okay, so this is really the impact of contaminants only on the way that crystals grow. Of course, they will also have an electronic effect as trap states and so on and so much. Okay, that was epitaxy in general, a very short, brief introduction. I assure you there's more to it. I want to move now in the direction of gallium nitride on silicon growth. For that, you should know there's a difference between homo-epitaxy, where you basically grow the same material on top of itself. It requires, of course, that you have native substrates, so that substrates of the starting material are available, which, for instance, for gallium nitride is an issue, but I'm sure Elke will discuss that in detail. Now, what we do in general is hetero-epitaxy, so we start with a certain substrate material and we grow all kinds of different materials on top of that. The nice thing is that you can form heterojunctions with that. Heterojunctions also were the reason for the Nobel Prize of Physics in 2000. They are the things that you need if you want to make things such as lasers or HEMTs or so on. You really need to have that technology. And of course, if you do hetero-epitaxy, you have to start thinking about strain management. So, strain. Imagine you have this existing crystal here and you want to grow materials on top that have a different lattice constant. So, for instance, in this case, it is larger. In order to make it adapt to the existing crystal, you will need to strain it. So, you will have to deform the crystal to make it match on this one. So, on the one hand, it can be compressive strain, in this case here, or it is tensile strain in the other case. And the important thing is to realize that it requires energy to do so. And as you build up layers of this strained material, more and more energy will be built up into this crystal. Right? So it's really a strain energy that is inside. Now you would say, okay, that's not a problem. The crystal can handle that. Now the problem is that it is not. So if you grow these strained materials, as you keep on growing, the energy that is built up in the strain grows and grows and grows and grows. So at first, this energy is used to just elastically deform the lattice, as we have seen before. But there is a critical energy when this energy will find other ways to be expressed. So we call it relaxation of the crystal. So you have a different number of forms to plastically deform the crystal and take up this energy. Now, what is plotted here is, in fact, showing that the moment that this plastical deformation happens, so the moment you reach this critical energy, of course, depends on how different the two different crystals are. So, for instance, this is the example of growing aluminium gallium nitride on gallium nitride. The more you increase the aluminium fraction of the argon layer, so the more you make them different, the sooner you will reach the limit where the deformation happens. So, for instance, growing pure aluminum nitride on gallium nitride, after 4-5 nanometers, it's already done with. Of course, with lesser, so if you work at 20%, 25%, you can grow much thicker layers. So this plastical deformation, it happens in various ways. In cubic crystals, this is the model of Matthews and Blakesley. It happens by, in fact, dislocations that are sliding over what they call glide planes, which are planes where it is the easiest to slide. And there's whole theories on how this happens. It's really half loops of dislocations that slide across, and then you end up in this case. And the end result is that you have a threading dislocation and edge dislocation at the interface between the two materials. So it's really a dangling bond in the crystal there. As I said, it is from cubic materials, so it is not the case for gallium nitride. And in gallium nitride, you have a whole different set of mechanisms. I think also here Elke will probably say more about that. Important ones that I will come back later is the bending of dislocations because of the strain, the surface roughening, so moving from a 2-dimensional growth to a 3-dimensional growth, and the formation of grooves in the surface. And also there I would like to say a few more words in a few minutes. I will focus on this one here, which is a cross-section TM of a typical AlGaN stack on silicon. So we start with aluminium nitride with very poor quality, and you can see we then grow up with different AlGaN layers that have less and less aluminium as you go up in the structure. And so here we do obviously hetero-epitaxy, so we grow aluminium gallium nitride on aluminium nitride, and you can see that the effect of the strain on the threading dislocation is that here at this interface where the strain is being built up, you bend your dislocation, and at the next one here it happens again, so it bends even further. And the advantage of this mechanism is that if you have two of them and they happen to be at the same place, they can actually meet and annihilate one another. So it is also a way to improve the crystal quality as you go up, which is the case in gallium nitride. So if you grow gallium nitride on silicon material, the starting layer here has a typical dislocation density of 10 to the 11th dislocations per square centimeter. And by this mechanism, by having them annihilate as you go up, typically the gallium nitride stack that's on top has already a factor of 100 less dislocations than it has at the bottom. But the example I really wanted to go into was this one here. It's again the growth of aluminium gallium nitride on top of gallium nitride, because this, as was explained yesterday and in the beginning, is really the core structure of your HEMT device. It is what you need to do. You grow a thin layer of aluminium gallium nitride on gallium nitride, and if you want to maximize polarization, you preferentially want to have a lot of aluminium in this layer. Now what you can see is that we have shown this critical thickness plot again before, that the way that the AlGaN relaxes in this configuration is not by this misfit dislocation, but it's by the formation of these grooves in the surface. If you look at a close-up of that, so the interface is not very visible here, but here is the gallium nitride, and then here starts the AlGaN. So the relaxation of this AlGaN that is under tensile strain there is really, it's a formation of grooves, so that you can see that the stress of the AlGaN that is being pulled at is really relaxing by these forms. This is a top view AFM of the same picture, so you can see that these grooves even preferentially follow the crystal orientations of your Wurtzite crystal. Now there's one way to prevent this. It is something we heavily promote at Epigant, so that's why it is in the presentation. And in fact, you can grow this passivation layer that I discussed already before, this in situ silicon nitride. You can grow it in your MOCVD reactor. And one of the nice effects of this, of growing the silicon nitride in your MOCVD reactor, is that the first few monolayers of the material are not amorphous, like what you obtain with PECVD silicon nitride and so on, but you can have some crystallinity. So if you remember the story I have told before on why a good passivation needs to have this specific atomic configuration, then of course having a crystalline starting layer there is beneficial. Now, what you also can see from this picture is that the silicon nitride, it can prevent the formation of these grooves that we have seen. So it also manages to eliminate this relaxation mechanism for the argon barrier. So in our experience, we have a product where we grow pure aluminum nitride barriers on the material. The only way to do that is by having this in situ silicon nitride material on top to stabilize the barrier material. And in fact, this is an illustration of that point. It is a very nice experiment where we have grown gallium nitride, aluminum gallium nitride layer stacks, and we have capped them with one monolayer of silicon nitride, one monolayer only. So that is half a nanometer. So it is not a lot of material. And what we did in the experiment, it was vary the time between the end of the growth of the argon barrier and the beginning of the growth of the in situ silicon nitride layer. And it is very clearly shown here that up to 1 minute at high temperature, your surface is stable, so you only see the atomic steps that you have before. But the longer and the longer you wait to cap your material, the more of these grooves form and the relaxation of your barrier occurs. I will skip this one, I think, because we need to go to the gallium nitride on silicon nitride. So gallium nitride crystals in nature you cannot find. It is very tough to grow pure gallium nitride material, so they are very small in size, and the cost is very, very, very high. So you need to look at different materials as a starting point. Typically, for LEDs, people work on sapphire, which works okay, but which has the disadvantage of a very low thermal conductivity. So for power electronics, it is not a good choice. You have silicon carbide that works very well, that is used typically for military and space RF applications. So it is relatively close to the gallium nitride material in terms of properties, but also the cost there is very high. Which leaves us with the last choice, which is silicon, which is the worst in terms of mismatches. So we have the lattice mismatch, but also the thermal mismatch. But it does have the advantage of the low cost and the maximum size of the wafer that you can use. So if you take everything into account, even though gallium nitride on silicon is the most difficult, it is the only economical solution that you have. Which is the same put here. So I have listed here the advantages of gallium nitride on silicon. So for instance, here you see the difference in cost. So a 4-inch silicon carbide substrate costs $2,000. Substrate alone, you have not done any epi on top of it. A 200 millican silicon is $30. So that gives you the range of the cost. Also important is that silicon is something that people that have a background in silicon electronics are more willing to accept into their fab because they're used to that material. And probably something that will be important in the future is that if you work on silicon, you open up a whole range of integration possibilities with silicon, something that you don't have if you work, for instance, on silicon carbide. Now, growing on silicon has one additional disadvantage. So we have done hetero-epitaxy. So I have shown you the problem you have with strain that you build up when you grow on top. If you grow on silicon, you have a second issue, which is the thermal mismatch, which is nothing different than the fact that if you grow these materials at very high temperature, after the growth, you have to cool down the materials, and the thermal expansion coefficient of silicon and gallium nitride are very different. So if you cool down, it's in this step here, you create a very large tensile stress. So what we need to do during the epitaxy is build in by designing our buffer layer stack, a significant amount of compressive stress, so that after we have grown this thing and cooled it down, in net, you have a flat wafer. Still, flat wafers is not a stress-free wafer, it is a stress-balanced wafer, which makes this wafers quite a bit more fragile than reference. You can actually monitor this while you are growing, which is depicted here. So we will grow this structure. We start from silicon. We do an aluminum nitride nucleation layer. We grow one argon and then a gallium nitride. The plot here, it's just an interferometer. So it is a red laser, and because of interference, you see how fast you are growing your material. So we see that you have different growth speeds for aluminum nitride, argon, and gallium nitride. And the plot here at the bottom is an in situ bow measurement. So it shows you, relative to this 0 level, how the bow behaves as you are growing. So first we have silicon, then we start growing with aluminum nitride. It creates a little bit of tensile stress because of lattice constants and the way it nucleates. And then every time you grow a new material on top that has less aluminum as the previous one, you are building up compressive strain until the end, where you enter growth and you start cooling down, and then the tensile strain goes in the other direction, so that again, net, we have a wafer that is more or less flat. This was my last slide. I think I'm pretty much in time. I had a few backup slides, but I think I will skip them for the occasion. So I do not know if there are any questions from the audience.
Thank you, Jof. Any question for Jof? Okay. But should be good if you, Philip, come here, you make the question from this side, so we can record also your question. Yeah. Also you, Peter. Yeah. Be quick.
Jof, thank you for the very nice explanation. I was wondering, the indium aluminum nitrogen layer, yes, you showed them as a lattice match, yes, at room temperature, but you're growing around at very high temperature. So how does that work? Probably related with the last things you explained. But
yes. It is true that probably the thermal expansion coefficients will not be very well matched, but the difference compared to gallium nitride and silicon are much smaller. So in practice, that is not an issue. It is only the lattice constant things that matter during growth, and then during the cool down, it is the main big difference between the nitrides in general and the silicon.
Thank you, Joe, for the nice presentation. I very much like your explanation of the passivation layer of silicon nitride. With the silicon, actually, the one layer of silicon atoms acts as the donors for the donor states. Yeah. So silicon oxide would then also work?
No, it would not. It would not, because I will go back to the slide. I need to scroll. There, because if you have silicon oxide, you're replacing this layer with oxide. So then you will have states, aluminum oxide, gallium oxide, yeah, instead of the nitrogens. You can no longer see this as a continuation of the 3-nitride crystal. It is then a 3-oxy-nitride crystal. It only works with nitride. Depending, of course, on what the states are, what an aluminum oxide or a gallium oxide do electronically in your band structure, depending on that. But the way this really works is because you can't consider it as the same crystal.
Yes. May I ask one more question, Chairman? Joe, in your view,
aluminum nitride.
No. In your view, 5 years from now, 200 millimeter GaN on silicon wafer, what would be the cost for a 600 volt buffer, for instance?
If you It depends on many things. It depends on the volume, depends on the tools that you can have. So if you extrapolate from today with existing tools, what they are, the cost to make them, you can get, I think, between $300 and $400. Yeah, for 200 millimeter. I think that is very possible. There is cost models that are provided by reactor manufacturers that are not always so accurate, but if you do the calculations yourself, that must be achievable. But the requirement is that it is volume production, so it is always the same product that you run day and night. If that is the case, I'm very sure you can do that.
Okay. Thank you very much. Joff, let's close this first presentation now, make a short break, 10 minutes, and we recover in 10 minutes from now. Thank you. Good.